In this lesson, we'll talk about antiderivatives and indefinite integration. Thus far in this course, we've talked about limits and derivatives, and now what we want to learn how to do is how to take derivatives in reverse. This is what we're going to call an indefinite integral. First off, let's just take an example here. We want to find a function whose derivative is 3x squared. Now, if you've done a lot with derivatives at this point, you can probably think about it and say, whose function was 3x squared? The function whose derivative was 3x squared was x cubed. And if you think about it, you can take the derivative, yeah, it is 3x squared. The function whose derivative was 3x squared was x cubed. That's the idea of antiderivatives. Indefinite integration, as we'll call it, is the reverse. Whose derivative is this function? Officially, the definition of an antiderivative is a function whose derivative is the original function. Capital F of x is often what we call an antiderivative. We usually use a capital letter compared to the original letter. And his derivative is the original function. We call it an antiderivative. And so one thing to point out is that say I had done x cubed plus 1, or x cubed minus 6, or other variations of x cubed plus any constant we want. The derivative of a constant is 0. So the derivative of each of these functions is also 3x squared. We don't have a single antiderivative. We have lots of antiderivatives. Let's look at this a little further. Here's a theorem that we can get actually off of Rolle's theorem, surprisingly, is that if we have an antiderivative of f of x, then what we get is if there's any other antiderivative, then that antiderivative differs by a constant. The reason this works is because if we assume that the derivative of a constant is 0, and we suppose that two functions have the same derivative, then we can prove backwards that since a function whose derivative is 0 must be constant, that any two functions with the same derivative only differ by a constant. What this boils down to is when we define the antiderivative, what we do is we let f of x be the antiderivative that does not have a constant, and we just write a plus c. This plus c is something you're going to become intimately familiar with. You do lose points if you don't write the plus c. You get the antiderivative of the function, just calculate it, don't worry about any constants outside, and just add a plus c. The constant we often call the constant of integration. Often we call it the arbitrary constant also. Let's do a few examples. F of x equals 3. F of x equals 3 is our question. I want to know what function has the derivative equal to 3. If you think about it, you might recall that the derivative of 3x was one way to get 3, and that's really the only way we have. So I'm just going to write 3x plus c. Note that this is a capital C that I'm writing. For this one, let me make a thought on this one. I know that x cubed would have come from a derivative of, say, x to the 4th. Remember, when we take derivatives, the degree goes down by 1. So let me just make a thought that the derivative of x to the 4th was 4x cubed. I'm kind of thinking about that in general. If x to the 4th was 4x cubed when we took its derivative, then the question is, well, how do we get just x cubed? And the answer is, put a 1/4 in front. Notice that if I have a 4 here, and a 1/4 was in front to start with, those cancel each other out and leave x cubed. With that said, 1/4 x to the 4th is an antiderivative of x cubed, so we write 1/4 x to the 4th plus c. Now these are a little bit tricky to just come up with right now. We're looking at it and saying, what can I possibly do with this? How can I just figure these out rapidly without putting some pretty high level of thought into it? Let's get some terminology together, and then we're going to learn a few rules. First off, the indefinite integral, which we write with this squiggly looking line, and I'll draw it on the board a few times so it makes sense how to draw it. This is actually a stretched out s for sum, which we'll talk about later. This is the antiderivative, the general antiderivative, the plus c. When we look at one of these, it simply means we're going to take the antiderivative. We're going to find the function whose derivative is what we're given. That's the indefinite integral. So anytime I say the word integral, that's the function whose derivative is what you're given. Let's talk about this notation a little bit. You've got the symbol for the integral, and you've got the dx. They are very, very important to keep together. If you do not write the dx, that's bad notation, and it will confuse you later. One thing to say now, always write the integral sign, always write the dx. The only time you get rid of them is after you've actually calculated it. One more thing that I sometimes say is think of this like a left parentheses, and this is like a right parentheses. We never have one without the other. One thing about integrals and derivatives, which are kind of nice, is that they are opposites, inverses if you will. If you take the integral of a derivative, you get the original function back plus c. And if you take the derivative of the integral, you get the original function back as it was. Let's start talking about some integration rules. First two that I give you are two that are kind of straight out. You've got the idea of adding or subtracting integrals. Now we know that we can add and subtract derivatives. We can take a derivative term by term. Same thing holds for integrals. We know that I can leave a constant in front when it comes to a derivative. I just leave it in front and take the derivative of the inside. But the same holds for integrals. And this particular rule will use a little bit more than just saying, hey, I can integrate term by term and keep the constants in front. That'll come in handy in its own right. Let's make an integration rule. To integrate 0, what function has a derivative of 0? A constant. I'll just say for some arbitrary constant c. Next one. Say we're integrating a constant. We integrated 3 earlier, and we got 3x. So as you might expect, you get kx plus your constant of integration. I'm going to write this as a rule. This is the first one that you should keep in your head, and you might keep this one also. We're going to have some rules for this. They're very important to have straight. Here's the rule that's a little bit on the tricky side. This one we talked about whenever I did x cubed, I got a 1/4 x to the 4th. And I will tell you officially, the rule is x to the n plus 1 over n plus 1 plus c. But this is only true when n does not equal -1. And the justification is similar to what I did for x cubed. I said I would take the derivative and reduce the degree by 1. If I'm starting with x to the n, the derivative would have been 1 higher before it was taken. The original function would have been an x to the n plus 1. If I were to take the derivative, the n plus 1 would come in front and cancel with this n plus 1 on the bottom. That's why I do the over n plus 1 to just get x to the n back. This is another rule I would have memorized. You need to be able to use this rule often, just like the power rule that we did for derivatives. So just to give you a quick example, I did x cubed and got 1/4 x to the 4th plus c. Another example could be, say, x to the -3. Well, that would be x to the -3 plus 1, we'll write it down, over -3 plus 1 plus c. If you do the plus 1s, you get x to the -2 over -2 plus c. So these are examples of just a quick use of the power rule. You add 1 to your exponent and divide by the new power. I will caution you in general, when you add 1, just pay attention to what you're doing. Make sure that you're doing your arithmetic properly, because with the negative numbers, people sometimes mess this up. Next rules. And these come straight out of your rules for derivatives, so you might even want to take a guess at these before I get started. Feel free to pause this video and ask yourselves questions like, which function has derivative cosine x? The integral of cosine x is sine x. And let me just make a comment here for the first one. Since the derivative of sine x is equal to cosine x, remember this is just the reverse process. Whose function has the derivative cosine x? Well, it's sine x. Whose function has the derivative sine x? Let me just make a comment here. We know that the derivative of cosine x is equal to negative sine x. We do know that. We do have a little bit of a negative sign issue, so we put it here as negative cosine x is your integral. Secant squared x, that's the derivative of tangent x. Secant x tangent x is the derivative of secant x. Cosecant squared x, well, there is a negative sign issue, but this is going to be negative cotangent x plus c. And this one is negative cosecant x plus c. But you should have these 6 rules in your head somewhere so that you can use them whenever they come up.
For e to the x, this one's actually kind of straightforward. Again, you're thinking about what function has derivative e to the x. Well, we know that the derivative of e to the x is e to the x, so that's actually our answer. It's just e to the x plus c. And again, that is since the derivative of e to the x is just e to the x. Now for a to the x, let's take a reminder for a second. Remember, the derivative of a to the x was the natural log of a times a to the x. So if we were to divide by the natural log of a, then this should work out. That gives us this rule, that the integral of a to the x would be a to the x over the natural log of a plus c. And then finally for 1 over x. You might think about it and say, whose derivative is 1 over x? The derivative of natural log of x would be 1 over x. However, there's actually a little bit more to it that we need to pay attention to. This rule actually ends up being the natural log of the absolute value of x. And there's a little bit of thought behind that. First off, this function is defined everywhere except for at 0. So my antiderivative should be defined everywhere except at 0. If I put the absolute value in, that allows it to be taken for negative values. But let's take a look at just why this actually works by taking the derivative of the natural log of the absolute value of x. We'll need to do this in 2 pieces. If x is greater than 0, we'll take the derivative of the natural log of the absolute value of x. We'll just end up taking the derivative of just natural log of x. Because remember, the absolute value is going to take a positive number and leave it exactly the same. That gives me 1 over x. Alright, what if x is less than 0? Then if you remember how absolute value works, it takes a negative number and makes it positive. The way we usually put that in our official definition is the absolute value of a negative number is just the negative of that negative number. And now we can apply the chain rule. The derivative of the outside would be 1 over negative x times the derivative of the inside, which would be 1 over negative x times negative 1, and that is 1 over x. So, the derivative of the natural log of the absolute value of x is indeed 1 over x, and so we will use this for our antiderivative in this case.
The rest of this lesson is examples. Let's do a few. The integral of x to the 5th dx. Let me just make a comment that n equals 5. You're going to do x to the raise the power by 1, divide by the new power. Every time, raise the power by 1, divide by the new power. Or if you like, add 1 and divide by the new power. For the power rule for derivatives, you had to do a couple of things with moving the power around and subtracting. This one, you're going to move the power around and divide. But again, add 1 to your power and divide by the new power. So that's my final answer. Now this one, I need to rewrite it as a power. Just like when we took derivatives, we needed some powers. So I'm going to rewrite it as x to the 1/2. Now, one very, very, very important notational thing. I did not take the antiderivative just now. All I did was rewrote it. Therefore, I left the integral sign and the dx. Don't remove these until you actually calculate the antiderivative. Now that I'm calculating the antiderivative, I'll remove the integral sign. I'm going to add 1 to the power and divide by the new power. I get x to the 3/2 divided by 3/2. And often we would write this as, instead of dividing by 3/2, we would multiply by 2/3. Your general dividing by a fraction is multiplying by the reciprocal rule. And there you go. Again, rewrite as a power. Use the power rule, which says add 1 to the power, divide by the new power. Next example, x to the negative 2/3. Already written in a nice form for us, so let's just add 1 to the power and divide by the new power. So we get x to the positive 1/3 divided by 1/3, which gives me, if I want to divide by 1/3, that's the same as multiplying by 3, 3x to the 1/3 plus c. This one I need to rewrite. Again, every time I ran into these with derivatives, I wrote them as a negative power. I need to do the same thing here. Again, I'm just rewriting. Right now I'm still keeping the integral sign, but in the next step I'm going to use the power rule, and so I no longer need it. So I get x to the negative 3 plus 1 divided by negative 3 plus 1, x to the negative 2 divided by negative 2, and for my final answer I'm going to write that as there's still a 2 in the denominator, but I'm writing the negative on top, and I'm going to move my x to the negative 2 down so that it's in the same form as my original answer. So again, there is a 2 in the denominator and a negative sign, so now there's a 2 in the denominator and a negative sign. X to the negative 2 I want to move down, so I moved it down as a x to the positive 2, and I just need a 1 as a placeholder there. This one's really easy, but we do have a constant in front, so let's pay attention to that. Constant in front just gets left alone, just like with derivatives. Integral of sine x, according to the rules that I just gave you, is negative cosine x plus c. So just to write a clean final answer right off the bat, negative 3 cosine x plus c. Next one. I included this one because this is the type of problem that students look at it and say, what? Officially, what this means is actually the integral of 1 dx. Don't let that confuse you. It really is just the integral of 1. With that said, the integral of a constant is that constant times x, so I just get x. 1x if you'd like. If you ever see an integral with nothing in it, that's what it means. First time I saw that, it confused me, so I figured I'd give it to you guys right off the bat. Now remember, we can take an integral term by term. I got a 2 in front, and then x squared. I'm going to add 1 to the power, so I get x cubed over the new power. Again, add 1 to the power, divide by the new power. Next term, I got a 5 in front. X, so add 1 to the power, divide by the new power. And minus 1 is going to become minus x. Let's clean this up a touch. Let's write this as 2/3 x cubed plus 5/2 x squared minus x plus c. For the next example, again let's take it term by term. I'll start off with the 3e to the x, so I'm just going to leave the 3 in front, and then remember the integral of e to the x is just e to the x, so that's not bad. And then minus, remember you've got an integration rule for a to the x, and a is just whatever the base is here. The rule becomes a to the x over the natural log of a, so I get 3 to the x over the natural log of 3 plus c, and we have this answer very quickly and easily. For this example, we're going to try a technique that we haven't used in a while. We're going to take this x plus 2 over x, and we're going to split it into 2 pieces. So what I'm going to do is do x over x plus 2 over x. Now in doing so, that breaks it up into 2 terms where I can integrate each term. Let's simplify it a little bit further. X over x is 1, and then I have 2 over x. Now, the integral of 1 is easy, that's just x. But then 2 over x. We need to think about what rules we had.
I did have a rule that the integral of 1 over x is the natural log of the absolute value of x. So with that said, I can do 2 times the natural log of the absolute value of x. The number on top, this 2 here, is just simply the coefficient of the 1 over x. And then I get a plus c.
Now this one, what I'm going to do is write it out. What does that mean? It means this. Now I will say I cannot take an integral inside the square or anything, just like you couldn't do a derivative that way. But what I can do is multiply it out and use algebra first. So again, I'm still rewriting, I'm leaving my integral symbol. First, x to the 4th. Outer, negative 3x squared. Inner is negative 3x squared. So I get negative 6x squared plus 9. Now I just use my power rule. X to the 4th, add 1 to the power, divide by the new power. 6 in front, right, add 1 to the power, divide by the new power. And then 9 just becomes 9x plus c. Let's write this a little bit better. I could leave it as x to the 5th over 5, and I do that often, but just for consistency with what else I've done lately, I'll write this as 1/5 x to the 5th. The 6 and the 3 cancel and leave a 2. And there's my final answer. You will notice that a lot of fractions come out of these problems, but there's not a tremendous amount of work to do with them.